Ready? Here are the terms. Here are the questions. Eyes up here. You have the answers on your paper from concept where they came back yesterday. What do you guys say for number 1? Atoms of one element change into atoms of another during chemical reactions. Loud and proud.
Never true.
Never true. Thank you. Atoms combine in 1-to-1 ratios to form compounds. Sometimes true. This is for you to make sure you correct it so you can study from this, okay? At Ishmael, we're starting with concept 4, okay? We're jumping in from stuff I came back yesterday. Number 3, atoms of one element are different from atoms of other elements. Always true. What's the big difference between them? Protons. Very good. 4, according to Dalton's atomic theory, atoms are composed of protons, electrons, and neutrons. It's never true. Dalton didn't know that crap. That stuff was like, that's new advancement, right? He was really, really kind of like 50 years ago or so. I might be wrong on that. 1800s. We didn't know much information at that point in time. Maybe some other people helped with that, but not Dalton for sure. 5, atoms of elements are electrically neutral. So, atoms of elements, okay, I can see why you guys said sometimes true. You're probably thinking, yeah. Yes, fine. Let me sign that real fast. In terms of the vocabulary there, it says atoms. It doesn't say ions. So I would say if I were just talking about atoms, I'd say, yeah, you're good in terms of always true. But yes, I can see where you guys maybe said sometimes true because ions are electrically not neutral. But I think we got the point there. 6, the mass of an electron is equal to the mass of a neutron. Say again? Never true. Okay, who weighs approximately equal? Protons and neutrons, but the masses of electrons are very, 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 very negligible. It's like 1/2000 of a proton. 6 is never true. 5, I said always true. Sometimes true if you're considering an ion, but that's kind of reading between the lines there. 7, the charge of protons, of all protons, is the same. Always true. They're all positive 1, right? 8, the atomic number of an element is the sum of the protons and the electrons in the atom of that element. Never true. The atomic number is just what?
Protons.
Just protons. 9, the atom of nitrogen has 7 protons and 7 neutrons. Sometimes true because isotopes, right? You can have different masses, hence different neutrons. 10, relative atomic masses are expressed in AMUs. Give me what you got. This one actually is truly always true because atomic mass is atomic mass units, AMU. We will eventually start talking about in grams per mole, but right now we're just talking about atomic mass units. 11, the number of neutrons in the nucleus can be calculated by subtracting the atomic number from the mass number. Always true. If you have the mass number, you're good to go. 12, in his periodic table, Mendeleev arranged the elements in ascending order of atomic number. So, I heard it never true. Why?
Because he did it in ascending atomic mass.
Yes, he did masses, and then another couple people came behind him and said, I think we should do this by atomic number. It didn't change a whole lot except for tellurilium. Just up here, table out. Tellurilium and iodine. Tell me what's different there. Look from like antimony, tellurilium, iodine, xenon. You can't see it up here. You gotta look on the periodic table because it's really tiny numbers. That goes in ascending what? Atomic number. This is the new modern periodic table, but what's different? You see, antimony is like 121, right? Atomic mass, and then tellurilium is what? 127, and then it drops back down to 126.9. So that's why there's a difference between the old and the new periodic tables. All right, and then lastly, a couple. What are we on? 14? No, 13. The representative elements are the group A elements. Yay or nay? That one's always true. Look on your periodic table, the blue one in front of you. Do you guys see where it says like 1? You should be looking at the periodic table in front of you. Okay. Do you guys see where it says 1A, 2A, 3A on the top of the groups? Okay, so that's 1A, 2A, and skip all the transition metals. Then you have 3A through 8A. Those towers are the representative elements. That's just their term. Everything here are the B elements in the transition metal area. Those are not representative because they don't have a representative kind of characteristic they carry. All of group 1 have a very particular characteristic kind of property that they carry versus like all the noble gases, oxygen's group, beryllium's group, and so forth. So those are represented because they kind of like represent, it's like they're talking about the whole entire group as a whole. They all have a characteristic in common. 14, the transition metals and intertransition metals are group B, always true. The elements in group 4A, period 3 is gallium. Who is it? Where's group 4A, period 3? It's like a map. Say again? So period 3 is sodium's period. Scooch over to 4A. Who is it? Silicon. Thank you. SI, silicon. So that's meaning you can read the kind of the coordinates of the periodic table. All right, and then let's quickly go through this. I think it's good to at least talk some of the conceptual stuff. Ready? 1, answer. Column A is matched with column B. I'm ready for you. T, thank you, 2. S, 3. R, 4. P, 5. 5. N, positively charged particles. 6. O, thank you, 7. Q, 8. I, 9. K, 10. M. Okay, if you're not checking this on your paper, I'm going to stop. Because if you're just looking and watching, it doesn't really help anything, right? You need to have like something to refer back to for your own purposes of studying, guys. Like, I'm not going to do this just for me. Number 11. J, 12. L, 13. D, 14. B, 15. H, 16. C, 17. F, 18. E, 19. A, 20. Thank you. All right, moving down to chapter 5, related information. Chapter 5, let's do a quick talk on matching, and then I'll take questions on the subatomic stuff, on the quantum stuff. You can see today what we're doing. Irie, what are we doing today? What are we doing today, Irie? Oh my gosh. Will.
Going over PS5.
Okay.
Valence, ions, and excited state.
Uh-huh.
Flame test lab.
Okay, flame test. Doesn't sound like you're going to use Bunsen burner. Okay, so I'm hoping to get there in less than like 10 minutes or so, okay? So let's finish checking up on some of the vocabulary part of chapter 5. Everybody has this in front of them. Everybody's checking and correcting. Okay. All right, so chapter 5, matching first. So 1, what do you guys say?
G.
G, good. 2, M as in macaroon. Okay. 3, F, 4, H, 5, I, 6, J, 7, N, 8, L. Very good, guys. 9, K, 10, B, 11, D, 12, E as an elephant, 13, C, 14. Wonderful. All right, down here, how many orbitals are in each of the following sublevels? So orbitals are the dashes we would draw. Sublevel is just the overall letter that we've assigned to that location, or the part of the orbital that we're looking at from the overall perspective of the atom. So 4p, how many orbitals would you have drawn there? 3. It doesn't matter if I'm talking about 1p, I'm sorry, there's no 1p. 2p, 3p, 4p, 5p, 6p, or 7p. It doesn't matter what the number in the front is. The number in the front's representing only what? So yes, so the period number, or the overall distance from the nucleus. So like the first energy level is right up next to the nucleus. Second energy level, third energy level, fourth energy level, and so forth. So that 4 doesn't really give you information about that question. It's just saying, hey, I'm 4 steps away from the nucleus. But overall, yes, there are 3 key orbitals in any key sublevel. 3D, how many orbitals would you draw here? 5, because all D block has 10 electrons across. That takes 5 orbitals to fulfill their spots. 4F, 7, because all of the F sublevel contains 7 orbitals total. How many electrons total is that? 14, right? 2 times 7 is 14. And then this S sublevel, just 1 orbital. That's the funny case where the orbital is also the sublevel. That's only because there's 1. Whereas this other one, you call it the P sublevel, has 3 orbitals, or the D sublevel has 5 orbitals. That's where the vocabulary comes into play. Yeah.
So there's 4 periods
Yes, the fourth shell away from the nucleus. Yep. All right. So 2, identify elements described above contains a full third energy level. Who do you guys say? Say again. Zn is who? Zinc, right? You say zinc? Okay. And that's because you have to consider where does the third energy level is, most times just the third period, but remember when we get into D block, we drop down an energy level? So it's like 3s2, 3p6, but there's the other 3 here, but where's it at? It's right here. There's 3d10. So zinc actually is the last part of the entire third energy level, despite the fact it's in the fourth row. It's simply because we assign a 3 to it there. Does that make sense? A little bit? Okay. Contains only 1 electron in the 4p sublevel. So gallium, because I keep looking at there. My parents always used to go there and can't see there. Gallium, because yes, it is the first electron or first element in the fourth period in the p area. Only 1 electron in the 5s sublevel. Rubidium, thank you. Contains 5 electrons in the 4s and 4p sublevel. Also arsenic, so you went over 2 and 2, or I mean 5, no 4. Over 2 and 4, and then over another 3, 1, 2, 3 in the p, but that gives us arsenic because there's 5 electrons total. Contains 3 electrons in the 4d sublevel. Say again? 3 electrons in the 4d sublevel. Neodymium, or navinium, sorry, navinium. Neodymium, navinium, okay. So you have to be in the 4d, so it's not the fourth energy, or fourth period, it's the 5th period, because when you hit D block, you do N-1 as your overall thought process. So yeah, niobium. Okay. Last one. Oh, no, not last one. 3, for each of the following elements, draw the orbital diagram, so you guys can do that. What else do I need to do? Yeah. Can I do carbon? Okay, so carbon. What's the electron configuration for carbon? You guys should be able to really quickly tell me those at this point. 1s2, 2s2, 2p, 2. You're stopping at carbon, right? You're not going all the way across to 6. So 1s2, you take the 1s information. You see that there's going to be a dash here to represent that 1s orbital. Can you guys see if I'm drawing on the board right here? Okay. And then there's 2 electrons there, so you draw an arrow up and an arrow down to represent the opposite spins. 2s, same story. 1 orbital holds both of those 2 electrons, 1 up, 1 down. How do you draw the p sublevel? Syrian? You have to do 3 dashes no matter if you're using them all or not. Good. And then? Bracket. Okay.
And then you have to do 1 of each first.
Okay. So just 1 up, 1 up. Good. So there's no doubling up anywhere until you exhaust the space, which we haven't exhausted yet. Good. All right. Another one from. I know I need to do the ions. I'm going to do that one of those examples. I'll do one of these. You guys tell me. 7. Which one? Oxygen, O2 minus. Because the only thing I didn't talk about extensively yesterday was the excited state, and then number 7, one of the ion states. That's why I'm going over this before I take this up from you, so hopefully you're with me here. I'll start with oxygen down here, and then I'll bounce back up to calcium. All right, so there we go. So what is the electron configuration of just straight oxygen? Yeah, that's how many electrons are present, but I want the whole electron configuration, like 1s2 and so forth, okay? So follow along. 1s2, 2p4. Okay, so you stopped at oxygen, it's about midway through the p block. So you can see 4, 2, 2, that is 8 electrons total. But then it told you O2 minus. What does that mean happened to this? So it has 2 extra electrons, which is why it has that overall negative charge. Where do you think those 2 electrons are going to have to go in our orbitals? Right, there's a maximum of 6 that can go into p block, right? So you got 2 extra spaces for those electrons, so then the electron configuration normal helps guide you to what the ion would be, because you went from 4, add 2 electrons to give yourself 6 there. So it's going to happen like that quite a bit. And I'll give you an explanation as to why. If you have 1s2, 2s2, 2p, 4, how do the electrons appear in this one? One up, one up, one up. Whose rule are we following? Huntsman's rule, and then we probably pair them up if we have to. There's 4, right? So you drop one like that. So I'm just doing half arrows, but they're there. So is there space for 2 more electrons? Absolutely, yeah. If I have the space and I can see it there, you can see that this electron's going to get added. That's 5. This electron's going to get added. That's 6. Okay, we're going over homework right now. So that's how you can actually predict ions that would form, where the electron configuration would change, and where the orbital diagram would change. They all kind of connect together. Yeah, Will.
What would you do?
Can you tell me what that one is?
Um,
What's the ion? I mean, what?
Aluminum.
Aluminum, what? 3+?
Yes.
Okay, so let me give you a hint on how these charges come to be, and then we'll talk about that. So there's this rule of science where the electrons that are within an atom, they will either be lost or they'll be gained. So we kind of knew that because you can form cations or anions. But like, what's the method to the madness? Like, why do some things form cations and why do some things form anions? Does anybody know anything about that? Cassandra? See, that's actually a misconception. Let me hold on that. So if it's losing entirely, then that electron's just not in the picture anymore. And so what you guys are thinking about, the electrons jump and then they fall, and they jump and they fall. They're actually not being lost. They're still there. So that's why trying to keep that in bubble. That's Bohr model, light, excitation, which is my next example. So I'm glad you said that. I'm getting there in a second. But just simply losing and gaining is like, what's the method to the madness? Yeah. Okay, I'm going to change that word to stabilization. Okay, so there's this word called octet. Write this down for yourself. Write this on your problem set or on your notes. So octet means I have 8 valence electrons. That's why you have your laptops. You guys are going to look at that in a second. 8 valence electrons. All right, so currently, plain old oxygen had, look up here at its electron configuration. We went over the word valence yesterday. What does the word valence mean? So the outer shell electrons, which in the case of oxygen, what's the outer shell? 2, the second energy level. How many electrons are here?
6.
4 plus 2 is 6 valence electrons. Good. Okay. So if I want octet, what does oxygen have to do? Gain 2 electrons to become 6 plus 2 is 8. So there's a method here, okay? So aluminum is my next example, I think is what we wanted. Let's go ahead and find aluminum. Write off the electron configuration first, and then we'll talk about changes. So aluminum, go for it, 1s, 2, 2s, 2p, 3s, 3p, 1. You guys with me? 1s2, 2s2, blah, blah, blah. We went to 3p1. We're right here. All right. What is the valence shell? 1, 2, or 3? 3. How do you know that again? Outer shell. It's the last energy level, or the most outer energy level. So if you had to circle the valence electrons, what would you be circling? Everything in the 3, right? Say again. 3p and 3s2. Don't forget that one, right? It's still in the 3rd energy level. Okay, so this is the 3rd energy level. So how many valence electrons are in the 3rd energy level? 3 valence electrons. All right, here's the predicament. Do I gain 5 electrons to get from 3 to 8? Or do I lose 3 to backtrack to fulfill the last octet I had before I added these extras? What do you think is easier for an ion, for an atom? Gaining 5 or losing 3? Losing 3. 4 is the break point, okay? Halfway between 8 is 4. Carbon's group, which is the 4th group, is the one that's like, oh, do I gain or lose? There's only ones that are like on the tipping point. Everything else is definite. If you have less than 4, you lose them. If you got more than 4, you gain them, because it's easier to get to one side or the other. So guess what happens to these? They get lost. if you lose 3 electrons, what charge do you become? Positive what? 3, Al 3 plus, which is the example that is on B of, was it number 4, number 5? Or 7? Okay, 7. So, the electron configuration of aluminum is what I had here in blue. The electron configuration of aluminum ion, Al 3 plus, is just 1s2, 2s2, 2p6, which was what was remaining after I lost those 3 electrons that were here in green. So, how is this stable? Why did it stop here and not lose them all? Anybody? Yeah. Great. So the second shell, so the 2s2, 2p6, that left me with a remainder of octet of 8 electrons. That's why it stopped there. Yeah.
So every time that we get ions, we try to get octets.
That's the only reason there's ions forming, is because sometimes with like 1 or 2 hanging out electrons in your outer shell, you're super reactive. So what happens is they either gain or lose electrons to form a bond, like an ionic bond. You guys know what ionic bonds are? They have ions embedded. We'll get there in like a couple weeks. They form this ion and then they bond, and then they're a happy couple, and then they stay there. Okay, they're very stable in that way. So there's more to this afterwards, but yes, you're right. Octet is the goal. All right, so take a minute if you need to talk to somebody on finishing up some of those problems in the problem set before I take it. I'll do excited state in like a couple minutes. All right, pause, come back to me. 5, 4, 3, 2, 1. Ready. Let's do calcium's excited state. Yeah, 1 second. So calcium, what's the electron configuration of just straight calcium? Ready. 1s2, 2s2, 2p6. So currently we are at neon. Move forward. 3s2, 3p6, and 4s2. Okay, that is normal calcium. This is calcium at ground state. Ground state meaning the most stable electron configuration. So, when electrons get excited, do they absorb or release energy? Absorb. What are some ways we can excite electrons? You guys did. Say again? Okay, so you can excite an electron by electrocuting it like I did the other day for you guys. Remember, we had the lights, we were throwing electricity at them, and then I had the high voltage source. So by electricity, what's another way to excite an electron? Say again? Heating them up like how? How? Fire! Thank you. Okay, so we're going to do that in a second. We're going to be putting them in the flame. And then another way to do it is shining really, really excited or high energy light. What's the highest energy? I won't say high energy light. What's a higher energy wavelength than just visible light? Ultraviolet. Okay, so you could shine UV rays or gamma rays or any other kind of high energy source on it and it will cause excitation. So those are facts you should know how to excite electrons. So when you do that, all you're doing is pushing something from ground state. Let's say this electron's like here. You're going to be pushing the electron out to an external higher energy level. So if I'm at 4s right here, I'm just going to say this is 4s. I know this is only 2, but if I was at 4s here, what would I be pushing the electron to? 5s, or it could be 6s or 7s, but generally we just bump it 1 energy level. Don't get crazy on me. So instead of calling it ground state like this, we would then say shift one of these electrons to a higher energy level. So I'm going to call that a 1 instead of a 2, and I'm going to shift 1 up to 5s, and there's only one of them that I've shifted. So basically, I'm showing that I'm going out of order. I'm skipping the whole fill up the 4s2 and putting one in a higher energy level, and that shows me, hey, there's still only how many electrons there? Total. 20. There's still only 20 because that's calcium's atomic number, aka electron count. So I haven't changed the element. I haven't made it an ion either. I've just excited it, and that's it. Okay? Question, Brandon?
So if it was like, let's say you were gonna excite it at 3p6, would you just use 1 and just make another?
I generally just stick with 1 because then we got too many like possibilities and we can maybe mess up. So if you want to excite more than 1, you can, but usually we stick with 1. Yeah. Radioactivity is more about its nucleus. We're going to get to that starting Monday. Okay? So it's more about what's inside. So we're sticking all about the electron, and then we're going to jump into radioactivity. All right, so let me pause for a minute because I feel like I'm losing some of you guys, and it's been 30 minutes or so. So how about we switch modes? Get a piece of paper out for the lab, and then we're going to come back and finish talking about this before I take this out. So our lab is called the flame test lab. So since we're talking about excitation, it makes sense for us to jump in here. I'm going to scroll really quickly to my instructions, and then we'll come back and do a couple more examples. So if you look on the board, that's what you guys just said. You want to go ahead and title this Flame Test Lab. I would write down your purpose or make a note to write the purpose. Okay, so we already know how to excite. That's what we're simply just like 30 seconds ago talking about. We talked about taking the electron from a ground state to upper level excited state. So you might use some of that as some description later on throughout the lab. But the lab itself, it's this. I'm going to demonstrate the first part for you. I'm not even going to give you the protocol, the lab instructions, because it's super duper easy. I'm simply going to show you how to get the flame test to work. Then I have a bucket for you guys with all of your samples in it. Your 7 or 8 different solutions. You're going to test and excite those electrons. You're going to see the color that's associated with that particular element. It's awesome. If you want to take pictures, that's fine. But hair back, I think everybody's got closed-toed shoes. I did not text you guys back or text that out to you guys last night, my bad. But let's work really carefully today. Let's go back to the lab in groups of like 3, okay? Groups of 3, back, go. Leave your homework on your desk. Leave your homework on your desk. I'm not going to take it out for like a minute.
Every morning I wake up and I don't know what's going on. I don't know if it's forever.
So you need to be spread out at all the lab stations because I do think that you need some space to work with. And I have one more thing. Sorry, I wasn't quite ready for this. I don't have everything on the desk yet. There's a little teeny stack, a half sheet on my desk. The half sheet is going to be a sheet. Alright, go ahead and set up your Bunsen burner. Don't wait for me.
Thank you. Will you pass that one over, right?
And you guys don't have goggles on yet, so send somebody to come grab goggles. If you do not remember how to set up a Bunsen burner, you need to pull out the instructions from below. Because I expect no flamethrowers. I expect that you know how to set up a Bunsen burner.
Yeah.
Do not strike your striker yet. I want you to set up your Bunsen burner.
Yes, you need to make that. Just made that up.
Alright, you should be set up in about 30 seconds, and then you're going to look back here, and I'm going to demonstrate how this works.
I literally just said make them
Do not strike the Bunsen burner just yet. Alright, and look at me in 5, 4, 3, 2, 1. Alright, do not strike the striker until I tell you to light your Bunsen burner. Thank you. So, you can see that I have this lit for this group. Lit, guys. Alright, so we're going to have, I have grabbed the one loop that does not have a little loop on the end. But, in this case, every single container has a loop. So on there is like it's a metallic stick with a tiny loop on the end. Do not mix these up or I will haunt you in your dreams. There's like 50 solutions and I have to make sure they taste the same because they get contaminated. Okay? This color that you see is very specific to the ions that are inside of the solution. So in your data table that I already passed out, you have a sample of lithium chloride, potassium chloride, copper 1 chloride, it has to be copper 2, sodium chloride, strontium chloride, and so forth. So on the data sheets, really the only thing you need information from, there is a lab protocol in some I think if you watch me, you'll be fine, okay? So all you're going to do is have an interblue cone in your flame. You're going to take the sample's lid off. You're going to dip your loop inside of your sample. just a little bit. It's going to get a little bit stuck in the loop. Now, I'm not going to probably so this works out well. You're going to then close this up because I've had spillages, and then you're going to hold your loop in the inner loop home, and so you should see a color. Yeah? Okay, this will brand somebody, so really carefully, do not, do not touch anybody with that. Let it cool. If you're like, oh, I didn't see the color, wink, wink. Okay, I didn't see it. Do it again. Okay, that's your goal. And don't hold it there forever because the loop will, you can probably see they're starting to degrade, they're starting to burn. So once you get like a color that's changed, probably because you burned off your sample, you need to use it. Okay? Now, almost everybody has all the samples, but like I only have like 4 potassium, which is a K. So if you don't have something at your table, it's probably the table next to you. So put it back in the rubber band, put it back in the bucket. At the end of identifying all the samples colors, I have about 12 unknown samples, which are here. Unknowns 1 through 12. You will identify at least 3 of them accurately, meaning do the ones you're really confident in, and those will be the ones I grade for accuracy. Okay? So other than that, are you guys okay? Okay, I'm going to help you guys identify again.
Yeah, but no, you guys tally. I'm not ready to count.
Okay, turn that off. Turn it off. Off. Great. I want you to tell me how you set this up.
I know.
Hey, you're turning off. Okay, turn it off.
Let's go with those. What is this? Alright. Ready? Yeah.
Sharing is caring. You make sure you share with the people next to you. So see how it's actually playing now? If you need to adjust.
I just noticed like and I'm like, oh,
So be careful when you're reaching across the Bunsen burner. I'm gonna put the lights down so you can see.
no, Hey, what was that? Yeah.
I'm gonna cut the lights down a little bit so you can playing.